Thank you very much for the introduction. So the context of this work is the transition to post-quantum security. We had a presentation this morning, and what we wanted to do with our work is to provide a tool for end users so that these users be able to use post-quantum secure products. So it happens that quite recently, the European Commission has edited a recommendation which aims at fostering the deployment of post-quantum cryptographic algorithms and the migration to post-quantum security. So we can see this work as a modest contribution towards this goal. So more specifically, our target is a VoIP application, which is based on the ZRTP protocol, where Z stands for Zimmermann, the inventor of PGP. So ZRTP is an authenticated key exchange protocol, and the corresponding VoIP application can be compared up to some extent to more popular applications such as Signal, WhatsApp, and others. But on a cryptographic point of view, all these applications, I mean, ZRTP and the other applications are very different. So ZRTP provides a key exchange phase, an authentication phase. The key exchange can be done in either two modes, either with Diffie-Hellman key exchange or with a pre-shared key. And in this work, we do focus on the DH mode since it provides forward secrecy. Regarding the authentication phase, this can be done either with signatures or with what is termed to as short authentication string, or SIS. This is a mechanism that I would call vocal authentication, but I will come to that in a moment. So after a ZRTP protocol run, session keys are outputs, and a second application layer, a second protocol must be keyed with these session keys in order to actually protect the voice packets. In the case of ZRTP, this second protocol is SRTP, which corresponds to Secure Real-Time Protocol. But again, here we focus on ZRTP. So how does look a typical ZRTP protocol run? It is made of three steps mainly. During the first step, there is a negotiation of cryptographic algorithms. There is also a packet in this step called commit that is involved in the authentication phase when signatures are not used. But I will come back to that packet to that message in a moment. During the second step, there is the actual key exchange, that is the part one and part two messages transport the Diffie-Hellman public shares. And in the last and third step, two confirm messages aim, as their name indicates, at confirming that the session keys are indeed shared by the two communicating parties. This is done because these messages are computed, encrypted and marked with session keys, not the session keys that will be used after to protect the voice packets, but with an independent set of session keys derived from the main shared secret output by the key exchange. So when authentication is done with signatures, the signatures are transmitted in the confirm messages. When authentication is done by means of this SS mechanism, the value that would have been signed is not transmitted, but is truncated to a very short string, 16 bits, and the two communicating parties start speaking together. So their voice packets are protected with the actual session keys, and then the two communicating parties will compare their own SS that they have completed on their own. The fact that this short 16-bit string be equal between the two parties, and the fact that the two parties do recognize their peer's voice, confirm that authentication is successful. So what we could say here is that a trivial attack in the middle would be possible because this SS is very short first, and an attacker behaving as Bob in this scenario could make a first key exchange with Bob to compute the first SAS value, and then could make a second key exchange with Alice. Since the last input to the key derivation is transported by the part two message, here, it means that in this scenario, the attacker chooses this last value. That is, the attacker has all the inputs and chooses the last one, all the inputs to the key derivation computation. So the attacker can compel Alice to compute the same SAS as Bob, And by doing this collision between the two SIS, the two communicating parties will think, because they share these SAS values, they will think that they do share the session keys, and more important, that there is no attacker in the middle. But in fact, they do not share the session keys, and there is indeed an attacker in the middle. So in order to mitigate this attack, here comes this message, the commit message, and this message transports, among other parameters, a hash of the value of this DH_part2 message. This means that the party that sends this commit message must compute the part2 message before receiving the part1 message. So in the one hand, the party behaving as Bob here must compute this part2 message before knowing the public share contained in the part1 message. And on the other hand, Alice here must send this part1 message before receiving the part2 message. All she knows about this message is the hash of this message, but based on the resistance of the hash function, she cannot get the explicit value of the message. So this is a way to thwart this actual attack. And this is why a very short string is enough to provide authentication in this case. This drawing depicts the computation of the session parameters. It is slightly simplified, but it depicts quite accurately what is done. So there are three main inputs to the session key derivation. The first one is the shared Diffie-Hellman secret. The second one is a transcript of the messages that have been exchanged so far. And the last one is a value called RS1, which comes from the previous protocol run between the two same communicating parties. From these three inputs, an intermediary shared secret is computed, and in turn, from this value, different session parameters are also computed. So the first one are the SRTP keys, which are used to protect the voice packets. The second set of session keys are used to protect the two last messages of the protocol run, the confirm1 and confirm2 messages. And the third session parameter is called SAS hash, and this is this value that is signed when signature is used to authenticate. This is also this value that is truncated when authentication is based on the SAS mechanism. And the last parameter that is output by the key derivation is the RS1 value, which is used to renew the current RS1 value and will be used in the next protocol run done between the two same communicating parties. So what we have done to transform this classical mechanism into a post-quantum secure mechanism, essentially, it is to replace the Diffie-Hellman key exchange with an ephemeral KEM exchange, and to replace the classical signature with the post-quantum signature. So since the current, at least many current users of this protocol are willing to continue using this SAS authentication mechanism, we decided to not remove this mechanism, despite we would prefer using only signatures. This is why the commit message is still present in the protocol flow here. So since this commit message must transport a hash value of the part2 message, it is not possible to send the ephemeral public key into the part1 message and to send the corresponding ciphertext into the part2 message, because in order to compute the ciphertext, one needs the public key in the first place. So the public key is sent in the commit message and the part1 in the ciphertext in the part1 message. More specifically, in the open source code that is provided, this is it's an hybrid KEM and an hybrid signature that are given, that are implemented. But the security proof that we provide, the security arguments that we give, allows to instantiate the KEM and the signature either with classical mechanisms, in this case, there is no quantum security, or with solely post-quantum mechanisms, or with hybrid mechanism, which is the case in the current implementation. So to enter a little bit in more details, the hybrid KEM is made by combining the classical KEM and the post-quantum KEM. The classical KEM is a DH-based KEM, and the post-quantum KEM can be instantiated either with Kyber, which is a futuronist standard, or with HQC, which is a code-based KEM, contrary to Kyber. and which is currently still in the competition of the NIST. And the combiner that we do use is given by Bandel et al. And it resembles more or less to the derivation mechanism that is used in TLS 1.3. So it allows to add yet another shared secret into the key derivation mechanism. The signature, the hybrid signature, is merely the concatenation of the classical and post-quantum signature. And we choose to instantiate LDSA and lithium, which is also a feature NIST standard. We also made other changes which are not related at all with post-quantum security, but which are related to security in general. These changes aims at mitigating issues or flaws that were raised by previous works or which remained unnoticed so far. So the first issue, the first change is to add into the transcript of the messages the very first message that is sent in the protocol run, the hello message sent by the initiator. And for some reason, in the original specification, this message is not included in the transcripts. This allows to make an attack described by Bhargavan et al. And with this attack, the attacker is able to change the cipher suites proposed by the initiator. So to be fair, the consequences, in fact, are rather low because there is no weak algorithm that is available in ZeroTP, but still it's cleaner to avoid such a scenario. The second mechanism, the second change is related to the way the signature is computed. In the current version, the signature, the value that is assigned by both parties is in fact exactly the same value. It's this parameter called SIS hash, which means that it is possible to make a trivial reflection attack. That is, the first party that receives the first signature can merely send back this signature, and the first to sign the SIS hash will receive back its own signature and will accept this signature as valid because it is indeed valid. So although it is very unlikely that such an attack be successful in real life, because that would mean that, for instance, Bob would accept himself as a partner, as a communication partner. So although this attack is unlikely to be successful, again, it's cleaner to throw out such a possibility. So to mitigate this scenario, we add a distinct label that is prepended to the value that is signed. And the label depends on the role, initiator or responder of the communicating party. The next change that we have done regarding the way the signature is computed is in fact related to one of the presentations that has been done during the first day of the conference. During the presentation made by Samet Düzlü, several security properties for signature scheme have been presented beyond the traditional regular unforgeability property. And among these properties, one is called exclusive ownership. And this is what is at stake here. The specification, the original specification, says that the signer must send the signature, and in addition, it must send its public key or a link to that public key. So although the specification does not explicitly allow this possibility, it may happen that this link, this reference, this identifier may correspond to two different public keys. And in such attack, that would allow misbinding attacks. And as explained by Samet Düzlü during this first day, a simple way to throw out such a scenario is to unambiguously incorporate the verification key into the data that are signed. So it was a transform proposed many years ago by Paul and Stern when they discovered this property. So this explains why we have done this change here also. And the last change that we have done is to change the way the confirm message are computed. They are computed with the symmetry key function that makes use of IVs. These IVs are generated pseudo-randomly in the genuine specification, which means that they must be transmitted. And instead of transmitting these IVs, we choose to compute these IVs as yet another session parameters. So this allows saving a little bit of bandwidth. So one could say, what's the point to save 16 bytes when the message transports signature that have a length of several thousand of bytes? Well, we expect that maybe there will be a signature scheme that will have much shorter parameters. We have had a presentation yesterday by Corentin Jeudi of this Phoenix signature scheme that aims at reducing the parameters among other security properties and nice features. And there is also this NIST competition regarding the signature, which aims, among other goals, at providing signatures with shorter parameters. So if these parameters, if the signature is lower than some threshold, saving 16 bytes would be interesting, at least in our case, because this would avoid using fragmentation. So we have analyzed this resulting protocol in a security model that incorporates several security properties. The first one is authentication, which means essentially that each communicating party that accepts, meaning which deems that the protocol run has ended successfully, it's such party as one unique partner. Key indistinguishability means that the session key is essentially good, that is similar to indistinguishable from random value drawn from the same set. Forward secrecy guarantees that the previous session are not compromised if long-term keys are disclosed. And finally, soundness or correctness guarantees basically that the protocol does what is supposed in the first place to do, that is, it guarantees that the two partners do share indeed the same session key. So we have used a model where the adversary can basically do pretty much anything but to leak the internal state. So it can control the network, it can corrupt long-term keys, reveal session keys. So it can do a lot of things as long as this does not lead to trivial attacks. So we provide a sketch of the proof in the paper and also the corresponding security bounds. The bounds are not tight. However, here our goal was not to reach tightness, but to highlight the underlying blocks which the protocol relies its security upon. And finally, we provide an open source code regarding the post-quantum schemes. The code is based on the Open Quantum Safe project. Note that the current version does not allow to authenticate by means of the signature, only with this SIS mechanism. So this open source code is available. Anyone can use it, modify it, etc. To sum up, what we have done in this work is to provide a post-quantum proposal to replace the current ZRTP protocol. Along the way, we have mitigated several issues and flaws that some of them were noticed previously and others were not. We have made a security analysis of this resulting protocol, and in the end, we have proposed an open source code that anyone can use. And before ending this talk, I would like to highlight the strong implication of my co-author, Johan Pascal, who did all the developments and who is currently maintaining both the classical and post-quantum version of the protocol. And I thank you for your attention.
Thank you for the talk. Then we do some questions.
Quick question. Obviously, MLChem, MLDSA become much larger. Does that cause you problems with fragmentation? And if so, how do you handle it?
Well, I don't know why in the first place their parameters would become larger, but if in such a case, that would be a question, to be honest, to Johan, the developer of the code. But I think that we could find a solution with fragmentation. Yeah, if we can avoid fragmentation, it's better. But with the current version of the code, we do use fragmentation, even if authentication is not done with signature, but we do use fragmentation because we have a post-quantum KEM in the name of Kyber or HQC, and the performance are very reasonable. So
you're using, depending on IP level fragmentation, is that correct?
Yes, I think so.
Yeah, it doesn't work everywhere, but oh well.
Well, what I can say is that the test and the experiments in real life that have been done, including with real life users, show that everything work pretty much.
Any last questions? So maybe I can ask a quick one, like for TLS, we see that the signatures give a lot of overhead, and there is some suggestions for using chems, like in ChemTLS. Would that make sense in this setting as well?
Sorry, I did not hear quite clearly the question.
To replace signatures by chems, like in ChemTLS, would
Yes.
that make sense in this framework as well? And would that give you benefits when it comes to sizes?
Yes, I think it would, certainly. The issue, in fact, is that how to manage the static public keys. The reason why so many users, current users, still want to maintain this SAS mechanism is because they want to avoid the burden of the public keys. But beside this, beyond this, yes, that would work. But then that would be a ChemTLS applied to VoIP.
Let's thank Loic again.